For VCE Algorithmics, we need to know about backtracking, hill climbing, simulated annealing, and A-star. Generally speaking, a heuristic is a fast way to generate an approximate solution for a complicated problem. Backtracking is best compared to brute force, where we explore all possible solutions to a problem and choose either the first one which works or the best one. For example, we could recursively generate all possible layouts for the n queens problem and choose the ones that work. For the traveling salesman optimization problem, we could find all possible routes and see which one is the lowest. However, when generating solutions, we might make one which is already invalid. If we have two queens on the same row column diagonal, or if our route is already longer than the previous best solution in the case of the traveling salesman problem, there's no point continuing. Backtracking checks our solutions as we go along and stops if it realizes the current solution is inadmissible or the partial solution will not lead anywhere good. Generally speaking, this should result in fewer solutions being explored before a valid one is found. However, it is conceivable that we could end up exploring most or all of the solutions already explored by brute force. It is also possible that the process of checking our solutions as we go takes up so much extra time that it cancels out the benefits over brute force. These are both unlikely but possible scenarios. Backtracking can still take quite a long time, particularly in the case of the traveling salesman optimization problem. Our next option is hill climbing. We start with a random solution and then make changes to it to see if it leads us to a better solution. If a change leads us to a better solution, we accept it and we keep going. If not, then we discard it and we go back. When it's no longer possible to move to a higher solution, we stop. This is a fast and simple heuristic, but it can get us stuck in local optima so that we never find the best solution. To avoid getting stuck in local optima, we can use simulated annealing. This is taken from the idea of metal cooling. We set an initially high temperature which reduces for each solution we try. When we try another solution, we accept it if it's better. If it's not, then depending on the temperature, there is a probability that we accept a worse solution, in the hope that this will eventually take us to a better overall optima. We might also keep track of the best solution found so far, so that we can go back to it if our subsequent jumps didn't lead anywhere good. Simulated annealing is good if we expect the search space to be unpredictable with irregular distribution of local optima. Our final heuristic is A-star and is a specific improvement on Dijkstra's single source shortest path problem. Recall that Dijkstra records the cost of each node as it goes along. A-star adds a heuristic which estimates the cost quickly from each node to the target. Using this heuristic means we don't explore so many paths which are not going to take us towards the target. The heuristic must be admissible, which is to say it must not overestimate the true distance. It can underestimate. For example, we can set it to 0 for all nodes, which means we're just running Dijkstra as normal, and it's okay if it's inconsistent. A suboptimal heuristic in this regard might take longer to get to the best solution. However, a heuristic which overestimates may not find the right solution at all. Remember, when answering exam questions, heuristics are not design patterns. If you have any questions, leave them in the comments, like, subscribe, all that stuff.